When we apply operations to sets, we form new sets. And usually one of the questions we are interested in is that when we form sets and we have different sets, we ask, are these sets the same or not? We talked already about the notion of what it means to be a subset, right? A being a subset of B. But what does it mean to have two sets A and B being the same? Okay, so the definition of equality of sets is as follows. Two sets A and B are equal if A is a subset of B and B is a subset of A. Okay, or in other words, if you look at any element, either the element is in both A and B or the element is in neither of them. Okay, so for all x is in A, if and only if x is in B. So we are saying you look at every element in the universe, either that element is in both A and B or in neither of them. Okay, so that basically when we list them, they should have the same elements. That's what it means to have equal sets. Okay, now how do we prove that two sets are equal? Again, it's based on the definition. We said A and B are equal if A is a subset of B and B is a subset of A. Here on this slide, I'm listing two important identities that we have seen in the context of, for example, propositional logic. These are called De Morgan's laws, which one of them says that the complement of the intersection is the union of the complements, and the complement of the union is the intersection of the complements. Okay, so how do I, for example, these are not axioms, these are theorems that we can prove. So for example, how do I prove this result here, that the complement of the intersection is the union of the complements? As I said, to prove this result, we have to show two parts. Okay, so the first part, I have to show that the left-hand side is a subset of the right-hand side. And the second thing, I need to show that the right-hand side is a subset of the left-hand side. Once we show both of them, then I have showed that these two sets are equal. Notice that on the left, number one here, if I show just this part, I am saying that the left is a subset of the right. That doesn't guarantee that they are equal because the right-hand side could have more elements in it. But then that's ruled out by proving also the point on the right, that the right-hand side is a subset of the left. So how do I show that the complement of A intersection B is a subset of the union of the complements? Well, we go back to the definition. What does it mean to have something A being a subset of B? It means that for every x, if x is in A, x must be in B. So we say that let x, suppose x is an element of the complement of the intersection. We need to show that x must be in the union of the complements of A and B. If x is in A intersection B complement, then by definition of the complement, x is not in A intersection B. Okay? If x is not in the intersection of A, x is not in the intersection of A and B, then x is either in A, x is not in A, or x is not in B, right? You cannot have x in A and x in B and still have x not being in A intersection B. So these are equivalent here, right? So this is equivalent to the first statement, and this is equivalent to the previous one. But what does it mean x is not in A? It means that x is in A complement, and or here x is in B complement. By definition of the union, this says that x is in the union of complement of A and complement of B. Okay, so again, I repeat that I started with this line here saying that let me assume x is in the complement of A intersection B. By definition of the complement, this means that x is not in the intersection of A and B. What does this mean? It means that x is not in A or x is not in B, because if x was in A intersection B, it means x is in A and x is in B. Using De Morgan's law from propositional logic, the complement of that is x is not in A or x is not in B. But again, using the notion of complement, This means that X is in A, the complement of A, or X is in the complement of B. And using the definition of union, I can get to X is in the union of the complement of A and the complement of B. If I want to show the other side here, that A complement of A union complement of B is a subset of the complement of A intersection B, I can actually show it directly, but it will be exactly the proof on the left, because there I'm using equivalence, and equivalence is symmetric. I can go from A equivalent to B, B equivalent to A. It's the same thing. But if I want to write it down, you will see now it's just basically the reversal of what I wrote on the left. I assume that X is in the union of the complement of A and complement of B. This means this is equivalent to saying that X is in the complement of A or X is in the complement of B, what means that this X is not in A or X is not in B, right? This means that, or equivalent to, X is not in the intersection of A and B, and this is equivalent to X is in the complement of the intersection of A and B. Again, if you look at them here, when we went from from top to bottom, this is exactly the same. You see it here, okay? So proving these two sides basically establishes that the complement of A intersection with B is the union of the complement of A and B. The same thing we can use to prove the other De Morgan's law, which I'm not going to show here, okay? But this is basically, these are important identities that we use. Another law here is that the complementation, the double complementation of A gives us A here, okay? And this is again similar to remember the negation, double negation of a proposition. P gives us the proposition. So how do I show this? Again, I can start by saying, let me assume that X is in the complement of the complement. This is equivalent to saying that X is not in the complement, right? Which basically means that X is in A. So again, going this way establishes that this is a subset of A, sorry, not of B, of A. And if I go from this way here, I am establishing that A is a subset of the double complement here. So this is a simple proof that the complement of the complement of A gives us A. And we have so many identities, and we can prove all the identities that we can come up with identities and prove them. But some of the identities that are useful and we use them in general, one is the commutative law, that you can swap A and B in the union. So A union B and B union A are the same. Same thing with intersection. There is the associative law. Sorry, it's not associate, but associative law here, that the union of A with B union C is that A union B, then union C. So we can take the associative law. The same thing with the intersection. Distributive as well. We can distribute across a union, and we can distribute across an intersection. These are very important identities. Again, I want to mention once more that these are not axioms. These are theorems that we can prove and establish their correctness.